Welcome everyone to Fieldstone King's College School and to our first lesson in grade 12 physics. So this is the very start of the dynamics units, and the first lesson is on motion and motion graphs. And this is mostly going to be looking at lessons that we've learned in grade 11 and just refreshing our memory on how things work. So to start off here, we're talking about kinematics, and if you remember, kinematics is the study of motion. And so in kinematics, we're just talking about position, velocity, acceleration, and we're ignoring the forces. Whereas with dynamics, which is the topic of this unit, we're studying, this is the study of the causes of motion. And here in dynamics, of course, we're going to be looking at forces a lot. We've got lots of forces to look at. Okay, so that's the difference between kinematics and dynamics. Dynamics includes some kinematics in it. Now, in this table below, we've got scalars and vectors, and we've got d, delta d, v, and a. So we're just going to fill this out, starting with saying what a scalar is and what a vector is. So a scalar has magnitude. Magnitude is just a larger word for size. So it has magnitude, or size, but no direction. And with vectors, so another way of saying that is that we have just a number and units. Whereas vectors, a vector has magnitude and direction. And the other thing to note here is that when you have a vector, the variables have arrows over them. And those arrows look something like this. If arrow was the name of my variable there, I would put the arrow like that. And, you know, some people will draw their arrows with two parts like that. That's fine. I write them like this. Okay. So, for our scalars and vectors, first we're going to look at d. And the scalar called d has the name of distance. So that's our scalar measure, distance. And what we can say about this is that it's usually longer than our displacement. I'm just going to put that onto the next line because it didn't quite fit. So it's usually longer than the displacement. And that's just because distance takes account the whole trip, and unless the distance is a straight line, it's going to be longer than displacement, which displacement is always the shortest straight line distance. Okay, so that's d, and d with an arrow over it, we call that position. Not displacement, we call this position. And of course, position has magnitude and direction. And it is the straight line from a reference point. Okay. So that's d. Delta d We don't generally talk about delta D in terms of scalars. So I'm just going to put a big cross through that. We don't generally look at that with scalar measures, but we definitely look at delta D, the vector. And this is the one that we call displacement. And so displacement is the change in position. Position says where something is. Displacement says how far something has moved. So the change in its position. So that's what we're going to put here. It's delta D is the change in position. And we can calculate that by delta D is equal to df minus di, where f and I mean final and initial. So our final position minus our initial position. Or if you prefer, you can write that as d2 minus d1. Both are fine. Alright, so moving on here, we have v. Well, as a scalar, v is speed. And that just tells us how fast something is going. Our equation for that, well, we have generally an equation for the average speed. So I've put v AV, or v average, it's equal to the change in distance over the change in time. Delta D over delta T. The vector is called velocity. And when we don't have any other subscript on it, just like over here I wrote v average, so I'll write v average down here. If it doesn't have that average, then like above, we've just written v here. Then we call this the instantaneous velocity. Which means how fast it's going right at that very second. Whereas the average velocity, well, we have an equation for this, delta D over delta T, and this is for average. Instantaneous, we can't really calculate without using calculus or without taking the tangent on a graph. Okay, A, we call this acceleration. And our average acceleration is equal to the change in speed over the change in time, delta V over delta T. And finally here we have vector acceleration, which we still just call acceleration. Notice it's the same name for the vector and the scalar when it comes to acceleration. But sometimes we'll say that it's vector acceleration. Okay, and our equation is, just like all the others here, the change in velocity over the change in time. Alright, so that's our table. That sums up the values that we're looking at here. Below here are just a couple graphs to refresh your mind on how these graphs might look. So here we have a position versus time graph and a velocity versus time graph. And those are for this situation over here, which is a puck sliding across the ice. So if we look at this, you can see that the position is changing at a constant speed. It's a straight line, which means that the speed is constant. If the speed's constant, that means it's a horizontal line. The speed is not changing at all. And if we were to draw the acceleration of this graph, well, we would have something that looks like this. Our acceleration would just be sitting right on that 0 line. We would have no acceleration because the speed isn't changing. Okay, now this second graph over here, you can see that we're looking at a pretty curvy position time graph. So we still have position and time. We can see that our position is changing quite a bit. Now, if we want to just find the average speed over some time period here, you can see that all we need to do is just take this position and do our delta D over delta T. we don't need to worry about any of this funny business going on in the middle here, this curvy bit. It's really quite simple to get the average velocity. We just take the first point and the last point. Excellent. Okay, so we'll turn on to the next page here and try a problem. It says that a jogger takes 25.1 seconds to run a total distance of 165 meters by running 140 meters east and then 25 meters west. The displacement is 115 meters east. Okay, so this runner has run 140 meters east, then 25 meters west. We've got our displacement. Calculate the jogger's average velocity. Now notice velocity, that's a vector. That means we want to say that v average is equal to our displacement over the time. Okay, and our displacement, we've got a few bits of information. Here we have the total displacement. It says the displacement is 115 meters, so we don't need to look at the other details, 165, 140, any of this. We can just say that our displacement is 115 meters east over 25.1 seconds. And that gives us a result of 4.58 meters per second east. And notice that in our problem we had 3 digits here, 3 digits here, so my answer has 3 digits. I'm making sure to follow the significant digits there. Okay, great. So there's our answer. Now it says calculate the jogger's average speed. Notice speed is a scalar, so we have v average. This is going to equal delta d over delta t with no vectors. So looking up again here, it says they ran a total distance of 165 meters. So we have that value, same amount of time, and we can find the answer pretty easily, 6.57 meters per second. There you go. That's that sort of a problem. Okay. We're going to take a look at the next topic here, which is the graphical interpretation of velocity. So there's a few pictures here. This first picture you might not be able to make out too well, but it's a car going along like this, very fast, in some dusty area. You can see all the dust and smoke that it's leaving behind it. So you have our car zooming across. Here's another sort of graphical picture of that. And you can see that the car's position changes by a small amount at first, a larger amount, larger and larger, which means that it's picking up speed, or it's accelerating. So our position versus time curves up like this. Velocity over time increases, means we have some acceleration here. So that's how we can interpret these velocity versus time graphs. Now if we want to find the average velocity from a graph, the average velocity can be found as the slope of a secant slope of a secant, and that's S-E-C-A-N-T, on a position time graph. So if we look at our position time graph, for instance, the one above here, and I say, here's my position at this time, here's my position at this time, and I want to find the average velocity, I take a secant, which is a straight line between those 2 points, and find its slope. And that will give me the average velocity. So secant is a straight line between 2 points. So we'll look at that again below. You see that we have this very changing position. We don't need to worry about those details. All we want for the average is to look at the start, look at the finish, and we draw our secant, a straight line. And to get the average velocity there, we just take the slope of that line. So that's rise over run. That gives us our average velocity. Okay, and in the picture to the right, you can see that the secants, if we take smaller and smaller and smaller time windows, eventually we get one that just touches the graph. And we call that a tangent rather than a secant. If it only touches the graph at one point instead of two, then that's a tangent, and that gives us our instantaneous velocity. It says at that very second, how fast are we going? And so that's on the next page here. Our instantaneous velocity, well, this is what we call just v, and it can be approximated. So it can be approximated with secants by making secants that are smaller and smaller and smaller, but the actual value is the slope of a tangent. And in this course, if you're ever expected to find a tangent, which we're not going to dwell on too long, we'll just look at it a bit in this lesson and not worry about it too much after this, but to find a tangent, the only way you can do it is by taking smaller and smaller secants or doing it graphically. What you would normally do is use calculus, but we haven't learned calculus yet, so you're not expected to be able to do that in this course. Good. Okay, so the next point here, what is a tangent? A tangent is a straight line that touches the graph at only one point. So it's like the secant, but it's just at a single point. And it gives us the slope at that very moment. Okay. Instantaneous speed, just like instantaneous velocity, the way we get that is the magnitude of the slope of that tangent. So that's how we can find the instantaneous speed as opposed to the instantaneous velocity. Alright, great. So here we have an example. It says the position time graph to the right shows the details of how an object moved. Calculate the average velocity during this time interval. So we have our time interval. From t1 is 1.0 seconds, t2 is 2.5 seconds. We want to get the slope. So average velocity, that's equal to the slope of the tangent, slope of the secant. So we have rise over run. Hopefully this idea of getting the slope should be familiar to you. So we have rise, we're going up 2, so that's 2.0 meters, and our direction here is to the right, so we're increasing by 2 to the right. And it's important that we have our directions in here so that our final answer has the direction as well. We're dealing with vectors here. Okay, and our run, that happens over a course of 1.5 seconds, 1.5 seconds. That gives us 1.3 meters per second to the right. Excellent. Okay, the last bit here, it says analyze the position time graph and use your analysis to sketch a qualitative velocity time graph of the object's motion. Okay, so we're looking at the graph here. This is the position time. You can see it does this funny business. And the question is, well, what does that actually look like for the velocity? Now, we're talking about just a qualitative graph. So the numbers, we don't need to have numbers on there. It doesn't need to be precise, but we want to try to get the right basic idea. So when we're drawing this sort of a graph, I've made my little Cartesian coordinates, but I'm only looking at the positive axis, so I don't need to show anything to the left here. So we start at time 0. We've got 1, 2, 3, 4. This is our time. That's t. Okay, and if we're looking above at time 1, you can see that we have quite a large velocity. And I'm doing that by looking at the tangent here. So we have quite a large velocity to start with. And you can see that our velocity is decreasing with time until 2 seconds where it's horizontal, which means that the slope is 0. So that means we're starting at some large number, and at that time 2.5 seconds, so we're starting at some large number at time 1, and by 2.5 seconds it should hit 0, because at 2.5 seconds we're level. Okay, after that you can see it continues decreasing for a little while, but pretty quickly it's sort of leveled out and it gets to 0 again. So that means that by time 4 seconds it should be hitting 0 again. So here we've got another 0, and then it starts increasing again. So we can continue sketching that. We've got another 0 here. So I said it starts here, it goes down, under, and back up. So something like that. That's the sort of graph that we're looking at if we were to talk about the velocity here. Good. And we'll just take a look at the very last page here, which is just about acceleration. It's the same idea. Acceleration, instead of change in position over time, this is the change in velocity over time. So the change in velocity over time. And our equation again is A average is equal to delta V over delta T. And again, this is an average, so we're talking about the slope of the secant. And instantaneous, just like with velocity, so this is the acceleration. At a certain instant. So we're not talking about averages here, we're talking about instantaneous, so at that very instant, how fast or how much are we accelerating? And we get this, again, by the slope of a tangent. And the other way would be using calculus, which we don't use in this class. Okay, so one last example here. It says, suppose the sprinter to the right is running a 100-meter dash. The sprinter's time and distance data have been recorded and used to make the velocity time graph to the right. Analyze the velocity time graph and use your analysis to make a sketch of an acceleration time graph of the sprinter's motion. Okay, we're just going to look at this quickly here. You can see that we have our graph. It goes up and back down. So if we want to make a little sketch of the acceleration, we want to figure out just the key points. So here, 0 movement, 0 acceleration, so it's going to be 0. Here, all of a sudden, we speed up quite a bit. And that continues. Here you can see that it's a very, very large, and then it starts to slow down again. And so by this point, we're back to 0 acceleration. I guess by this point, we're back to 0 acceleration again. And then just before 10 seconds, we start decreasing, so we have a negative acceleration. And then we start leveling off again, and somewhere over here we're going to get back down to 0 acceleration. So if we're really looking at this, we've got our acceleration time graph. This is 0. And we said that somewhere around, well, actually, I won't make that 0. I'll just say here, we've got 0 acceleration, and then at time 0, this is 0 here, our acceleration goes up quite a bit, and then it starts going back down again, back to 0. And then we're at 0 acceleration for a little while. We carry on. And then just before 10 seconds, so if this is 10 seconds here, just before 10 seconds, we've gone up again and back down. And that's our acceleration. That's what that looks like. Although, oops, that last one there, we don't go up. You see that it's getting very, very negative and then positive again. So we go down, then back up. Okay. That's our acceleration. The next one here says, from your acceleration time graph, determine the maximum acceleration and the time at which it occurs. I think we're going to skip that. What you would do is, you would look at this point, the maximum acceleration. You would try to find out approximately what time it happens here, and you would do some secants here to try to figure out exactly what the slope is there. But we're not going to worry about that too much. If you're interested, I would say that it's about 10 meters per second squared at around a time of 1 to 2 seconds, somewhere in there. Great. At the bottom here, we have a few homework problems to try out. So go ahead and take a look at those, and I'll see you in the next lesson.